In order to talk about dimensional analysis in physics, we need to first start with the idea that every measurable quantity in physics has itself a dimension with corresponding units. So for example, the quantity of length has a dimension of length, which we'll denote here as square brackets capital L, and it has a unit in the SI units as meters. Similar for time and mass have dimensions of, well, time and mass, respectively, and their corresponding units, seconds and kilograms. Sometimes we will talk back and forth between dimensions and units. We're really talking about the same things, although we'll try and stick with dimensions itself. What about other quantities? Well, other quantities in physics can be defined in terms of these basic dimensions. So here we're just sticking strictly to motion, and so let's talk about the next quantity we usually talk about in physics, which is speed or velocity. So a speed is a change in position over a change in time. So the dimensions of speed are the dimensions of change in position, which are length, and dimensions of change in time, which is time. So the dimensions of speed are length per time. And that matches what we expect, that the units for speed are meters per second. Same thing for an acceleration. An acceleration is a change in velocity over a change in time. And so the dimensions of acceleration are the dimensions of velocity, length per time, over the dimensions of time, which is time itself. Or combining the dimensions of time in the denominator, we get dimensions of length per time squared, which matches the unit that we expect for acceleration, meters per second squared. What about force? Well, we know that the unit of force is a newton, but what if you don't remember how to define a newton in terms of these other quantities? So how would we figure that out? Well, you just need to remember that force F is equal to ma in Newton's second law, and that will allow us to find the dimensions of force. The dimensions of force then are the dimensions of the mass times the dimensions of the acceleration. And so that is the dimension of mass itself times length over time squared. And so those are the dimensions then of force. That tells us what a newton is in SI units, because we just replace dimensions by their corresponding SI units. And so we get 1 newton is 1 kilogram meter per second squared. Let's now use dimensional analysis to solve some physics problems. Let's begin with this question. We have a ball on a string, and it's spinning in a circle of radius r with some speed v. And we want to know, what is the tension in the string? To use dimensional analysis to try and find out the answer of this question, rather than setting up Newton's laws and solving for the tension in the string, what we're going to do instead is we're going to make a guess that the tension, F sub t, is some combination of the quantities that are involved in the question: the mass, the speed, and the radius. And we're going to put each of these quantities to some unknown exponent. So mass to the a, some unknown a, speed to the v, b, and radius to the c. And we're going to use dimensional analysis now to find the unknown exponents. The way we're going to do that is we will set the dimensions of the left-hand side of this expression equal to the dimensions of the right-hand side of this expression, and hope that we can then solve for the unknowns a, b, and c. In order to do that, we first need to know what the dimensions of tension are. Well, the dimensions of tension are the same as the dimensions of force. And we remember that the dimensions of force are the dimensions of mass times acceleration. And so we need to put the dimensions of mass times length over time squared for our dimensions of tension. Using that, in our guess, the left-hand side has dimensions of mass times length over time squared. The right-hand side has, well, writing these out, the dimensions of mass to the a, and the dimensions of speed is now all to the b, so that's dimensions of length over time all to the power b, and the dimensions of the radius to the power c, which is the dimensions of length to the power c. And what we'll do is we'll match the dimensions on both sides. So, for instance, on the left-hand side, we're going to find that the mass dimensions on the left-hand side is 1, and on the right-hand side, the mass dimension is a. So that tells me that 1 is equal to a. or namely a is equal to 1. So we've found one of the unknown quantities. Let's do the same for time. So on the left-hand side, I have time in the denominator squared, so that'll be to the minus 2. And then on the right-hand side, I have time in the denominator all to the power b. And so I'll have minus 2 is equal to minus b, or just getting rid of the minus signs, that means b is equal to 2. Finally, let me use length on both sides. So if I match the length dimensions on both sides, I have the length to the power of 1 on the left-hand side. On the right-hand side, I have length that is coming in from two different places. It's coming in from length to the power b and length to the power c. So I must have that the 1 on the left-hand side is equal to b plus c. Well, using what I know about b, that tells me that c is equal to minus 1. Putting all that together, I have a to the power 1, or a is equal to 1, b is equal to 2, and c is equal to minus 1, so I get mv squared r to the minus 1, or mv squared over r. Hey, that looks familiar. That looks like something we've seen in circular motion before, except now we didn't have to do the work to derive it. We just used dimensional analysis and came to it right away. Let's do another example. Let's consider a ball swinging back and forth at the end of a long string. And what we want to know is what is an expression for the period t of oscillation? Well, the first thing we need to remind ourselves is, what is the period again? So remember that the period is the time it takes for something to swing back, or for the pendulum here to swing back to its original position. So the units of period are the same as the units of time in this case, which in fact is helpful since they both have the same expression here, a capital T. Now we need to make a guess. But in making a guess, we need to figure out what variables could be involved. In the previous example, I gave you the variables that could be involved, but here we have to figure out what they could be. Well, let's think. The mass seems like it should matter. The mass of the ball on the end of the string. Maybe the length of the string. And if there wasn't any gravity, then there would be no oscillation back and forth because the oscillation is happening because of gravity. So there must be something to do with the gravitational constant, little g, which is around 9.8 meters per second squared here close to the surface of the Earth. And I can't really think of too many other things that could be relevant. And so we would then make a guess that the period is written as mass to the power a, length to the power b, and gravitational constant to the power c, where a, b, and c are all unknown. Converting that into dimensions, that says the dimensions of time on the left-hand side are dimensions of mass to the power a, dimensions of length to the power b, and dimensions of length per time squared all to the power c. Well, now we can do what we did before and match powers of dimensions on both sides. If we match the powers of the dimensions of time on both sides, on the left-hand side we have 1, and on the right-hand side we have t to the minus 2 all to the power c, and so that's 1 is equal to minus 2c, or c is equal to minus 1/2. On the left-hand side, we don't have any powers of mass, and so we would say that that is a power of 0 on the left-hand side for mass. On the right-hand side, we do have mass to the power a, so it must be that 0 is equal to a, or there is no dependence on mass. That's actually a pretty cool observation that we made just using dimensional analysis. There's no way for us to include mass in a way so that the dimensions work. So the period of the pendulum must be independent of the mass. That's pretty cool. Finally, matching dimensions of length on both sides. On the left-hand side, there is again no dimensions of length, so that's a 0 for the left-hand side. On the right-hand side, we have length to the power b and length to the power c, so we should write 0 is equal to b plus c. We already know what c is, so rearranging this, we find that b is equal to positive 1/2. So now we can use what we've learned to write the period in terms of the mass, the length, and the gravitational constant. In particular, we found that the a was equal to 0, b was equal to 1/2, and c was equal to minus 1/2. So we should have the period is equal to m to the power 0, l to the positive 1/2, and g to the minus 1/2. And that tells us that the period, combining things and turning that 1/2 into a square root, the period can be written as the square root of L over G. We found an expression for the period using only dimensional analysis. We didn't have to use any other physics. And that's pretty cool. Well, this isn't exactly correct for the period. It turns out that the actual answer has a factor of 2 pi out in front. But otherwise, we got everything right. In fact, we even got the fact that the period is independent of the mass right. And that's a pretty significant observation about the period of a pendulum. So just note that since we didn't get the factor of 2 pi, well, dimensional analysis can't tell you about numerical factors because numerical factors don't have dimensions. And so dimensional analysis is only good up to some numerical factors. But it can get you the functional dependence of all of the other variables correct.